How you doing? I'm Mr. Rose, and as you can see, we're going to talk about a physics fan favorite, the box on an inclined plane. That's right, we've all seen this in introductory physics. It rears its ugly head in AP physics. This is not the easiest problem, but we definitely get a little bit more difficult on this side as well. So take a minute, take a look at this problem, write down all our givens, and we're going to get right back to it right at that board behind me. All right, so I've got a picture already prepped up, and here again, theta is 30 degrees, the mass of that block is 100 kilograms, and acceleration was 0 meters per second squared. What does that mean? The acceleration being 0 meters per second squared means this crate is doing one of two things. It is either moving at a constant velocity, or it's at rest, which both say have an acceleration of 0 meters per second squared. So I do want you to keep that in mind as we work through our board. Now, my board is not very big, and we will get into free body diagrams. Those are really important. This is going to be the first time we're going to kind of put one together, and I'll point out some differences between what we're doing and what an actual free body diagram is. Now, by definition, that free body diagram is a diagram with all real forces, which means the only thing that would be acting on a free body diagram is the force that was given. That's what we're looking for. This crate obviously has a force due to gravity that I'll call mg, like so. And it's not falling down through this. It's being held up by what I'm going to call the normal force. So those are all things that hopefully you can see, and that should be familiar. Now, those are all of my actual forces. That's it, because we're neglecting friction in this example. So this is what would be our free body diagram. Now, I'm going to put it down here, and then I'm going to add extra forces. Those extra forces are what we're going to need to solve it. So I'm going to take my box, and I'm going to make it a dot, just like so. And I'm going to put those forces that we just identified. And now I'm not the best at drawing vectors proper length when I'm kind of doing this out, so bear with me on what the drawing is going to look like. But now we need to break them into components. I have my force due to gravity, my normal force, and this F parallel, and they don't really look like they're on the same plane. So one thing I skipped here is I skipped drawing my X and Y axis. Now, normally we have an X and Y axis like so. I'm not going to use something like that. I'm going to use a skewed axis, which means I'm going to tilt to match what this plane is. And you're going to see why. So somewhere on your paper, I would usually put it on the right side of my paper, but I put that stuff over here. I'm going to put this coordinate system, X and Y. Now that means that skewed coordinate system, the normal is in my XY plane. That means MG and F are not in my XY plane. Now, we're going to start doing some similar triangles out here. Now, it's easier to see on this, but I'm going to put it down here. This normal force, Newton's laws, has an equal and opposite force. Now, if this F wasn't there, that equal and opposite force would just be what we call F perpendicular. Now, this force is here, so this should actually be bigger, right? So it's just, again, I'm trying to sketch things, but because this force is here, my normal force is going to be kind of skewed. The thing that hasn't changed is mg. So now, there's also a component like this box. I'm going to say wants to slide down. We know the box doesn't actually want to do anything. It's a crate, it's a box. Can't want anything. But this crate could slide down that slope. Sliding down that slope is something, I'm not sure, you can't see that green marker. Let's see if this one shows up. Perfect. This is F parallel, and we call that F parallel. It is the parallel component to gravity, the perpendicular component to gravity, and that gravity is my mg, mass times gravity. So those all play together, and those things fit my X and Y axis. Now this angle here is theta. Through similar triangles, this angle that I just put in here is also theta. So that's what we got going over there. Now, I know that this block is not sliding down, right? I said, oh, I don't actually, you shouldn't say that. I don't know it's not sliding down. I know that its acceleration is 0. So it's possible that it's moving down at a constant velocity. That doesn't matter for my free body diagram. What matters is this component, this F parallel, has to have something that is equal and opposite to it, which means there should be something in that direction. So I'm going to put that over here, and I'm going to call this, I'm going to put a little FP. I don't like that as a push force, but I'm going to label it FP. And now this is going to be FP with those two little parallel. That's weird. FP parallel. It is my opposite to that guy. So I know that and that have to add up. My net force has to add up to 0. And now I have this also, oh, that's the wrong direction. That is a very badly drawn vector, but this is FP perpendicular. So now I can start summing up my forces. Remember, Newton's law, all of the forces, mass times acceleration, the net force equals ma. We know that our net force has to be 0, but we also know that vectors can only play in the same direction, meaning I can only deal with the normal force, that F perpendicular and that F perpendicular at one time. This F parallel and that F parallel at one time. And even though it looks more complicated now, my skewed axis, I have the green one, the purple one, those two black ones all fit on that axis. One thing I skipped, this is also angle theta. That's again another similar triangle. So now my goal in this problem was to find out what F was, and I actually don't remember the second part, I wrote it down. Oh, and what the normal force was. So the first thing we'll do is find F, and to do that I know F net equals ma, and I need to figure out what directions I'm going to work with. Well, the directions I'm going to work with are going to be the up and down, the incline direction. Well, why am I going to do that? For two reasons. One, I only got two forces, so that makes it a little bit easier. Two, I've got no idea how, actually it doesn't really matter which one I do first, but I have no idea how I want to deal with all three of those forces, so it's just going to be easier for me. And you'll see why we actually have to do this first, part A. Find out what this F push is. So, let's see, in the, what I'm going to call the X direction is F parallel and F push parallel. So, in my X direction, I'm going to have, this is going to be mg sine, yeah, that's going to be mg sine theta. So, F parallel is equal to mg sine theta. And this FP parallel, that looks like, FP parallel looks like that's going to be F push cosine theta. Now there's a mistake written on this board. Have you caught it yet? If this is my positive x and this is my positive y, that means F push parallel is positive. Mg sine theta has to be, yep, you got it, negative. So that's a negative, and when I add those two suckers together, they have to add up. F net equals 0. So I'm going to say Fp cosine theta. It is really, I always like to add vectors, so I'm going to say plus a negative, which we know is just going to be minus. So I'm going to say minus mg sine theta. That whole thing is equal to 0. And now I know m, I know g, I know theta, I know theta. I can solve for F push. So let's see. That means my general solution is going to be Fp equals mg sine theta, that whole thing, divided by cos theta, and you may remember identity sine theta over cosine theta is tan theta. So my F push is going to be mg times the tangent of theta, or if I do it, now you want to make sure your calculator is in degrees. I got a force of 57.7. Wrong answer. Don't do what I just did. I didn't multiply by 9.8. Again, in our class, we can actually use 10. That 57.7 was incorrect. Do this one more time. That looks a little better. That is a force of 565.8. So this F push is 565.8 newtons. Now, this part B, and I can fit part B here, though I don't like to do things like this. Part B was, what is the value of the normal force? Now, we should know that, let's say I have a weight of 600 newtons, hypothetically. I'm pushing down on the floor, 600 newtons. That means the floor is pushing up on me, 600 newtons. That's true. But here, if this wasn't there, as I increase an angle, increase. So this marker is going to represent my normal force, and you can see the normal force is no longer straight down. Eventually, so it's perfectly vertical, there is no normal force. So as my angle increases, the normal force should decrease. But I'm literally pushing this into the plane of the ramp. So the normal force has to be bigger than my weight. Well, again, we're going to do this the exact same way, except looking at my diagram. Here, now I'm going to say my normal force. You know what? I'm going to do the whole thing. F, what is in the y direction, is equal to the normal force minus FP parallel minus, oh, I call that parallel, sorry, perpendicular minus what is normal F perpendicular, that guy there. Positive direction, negative direction, negative direction. I know the sum of all those forces equals 0. Thus, I can say that the normal force is equal to FP perpendicular minus, did that right? And plus, there we go, regular F perpendicular. Whew, that was close. That and that are in the same direction. I could bring that aside, negative, 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 or positive, positive, positive. I like my positive numbers. Now, what is FP perpendicular? This is going to be F push, which I just figured out, sine theta, plus that guy, which is in the, I'm lying, plus that guy, F perpendicular, which is mg cosine theta. I now know what F push is, sine, cosine. I should be able to figure that out. Let me grab my calculator here, and hopefully you know things like sine of 30, cosine of 30, sine of 60. Those are all things that we should have committed to memory. If not, it's okay because obviously your calculator can do them as well. So let's see, I've got 1,131.6 newtons. FP equals 1,131.6 newtons. Now I know you all have paused and done this yourself, and my video is paused. Often I would edit things like that out, but I thought that was kind of funny, so it's going to be in there. Anyway, FP, 1,131.6 newtons. Now, we may have a couple of different answers. Like I said, I know you did this before you watched me. Some rounding errors. If you used 10 instead of 9.8 meters per second squared, will be slightly off. One thing that I love about physics, especially at this level, sig figs, no one really cares about that. What do I mean by that? Well, I gave you 100. There's no decimal point. That's a different significant figure. But since this has 3 digits, I call them 3 significant figures. I can make them significant. This could be written as 1,130. I wouldn't mark that wrong. The AP won't mark that wrong. 1,131 would be fine. Generally speaking, if I can, I try and carry 2 decimal places. But as you know at this point, these big numbers, these relatively small numbers, or 0.6 to 0.4, when we're talking about something that's 100 kilograms, we never know the difference. Anyhow, that's all I have for you. I hope you enjoyed my mistakes. I hope you enjoyed when things were frozen. Things are frozen. I'm not a ventriloquist. Anyway, please feel free to like, click, and subscribe, and you will see me next time.